Butterworth filter, as well as we derived the expressions for the gain as well as the frequency of the filters. We'll take few problems on the same and then we'll go for the next. So here is to calculate the values of the resistance required in a second order low pass Butterworth filter having a cutoff frequency of 15 kilo radians per seconds with a capacitance of 0.02 microfarad. So we have deduced the expressions in the previous class. The higher cutoff frequency fh is equal to 2 pi r1 r2 into c1 c2, and I said in the previous class all the resistance and capacitance used are same, then the frequency equation will be fh is equal to 2 pi rc. Substitute all other values and calculate the r here. So you will be getting r is equal to 3.3 kilo ohm. Okay, next, second problem is of similar kind. So it is also design a second order low pass filter for a cutoff frequency of 100 kilohertz and draw the circuit diagram. Draw the circuit diagram. So here cutoff frequency they have given it as 100. Cutoff frequency is 100 they have given, and also you have to assume the capacitance value if they are not given as very smallest values. It is 0.1 microfarad I have taken, and all the resistances are equal, that is R2 R3 is equal to R, C2 C3 is equal to C, and also assume R1 is equal to 10 kilo ohm, and just from the equation of the frequency fh is equal to 1 by 2 pi rc. So substitute all the other values and calculate r here. Okay, now for second order Butterworth filter, it is always Rf is equal to 0.586 into R1. This is a standard constant value. So just Rf is equal to 0.586 into 10 ohm you have assumed here. Substitute, you will get Rf is equal to 5.86 kilo ohm. Okay, and in the problem they are asked you to draw the circuit diagram. So you have to draw the circuit diagram and you have to put the values of Rf, R1, capacitance value in the circuit. Okay, this is about the second problem. Now next type of the filter is first order high pass Butterworth filter. Okay, so it is also order of the signal which we are using is of this one, that is why it is a first order. That is why it is a first order low pass Butterworth high pass. The previous section we have discussed is low pass filter and it is a high pass filter. Okay, so this is also realized using a RNC network. This is a schematic representation, schematic view of your high pass filter. Here it is as a filter is a high pass filter, which will passes only higher frequency signals and blocks the low frequency signals. Okay, so here the pass filter that attenuates all the signals below the lower cutoff frequency and also only high cutoff frequency. That is what as I said, the first order low pass filters can be obtained once again using the RNC element. So this is equivalent circuit of this one. Okay, next from the figure, it is once again its derivations are similar, all these derivations are similar. So first you have to calculate the potential at the terminal A, that is VA. So here same VA is equal to Vin into, according to the potential divider rule, you can calculate here R. See here we have, so R Vin into bracket of R divided by R minus JXC. This is according to potential divider rule. Okay, just Vin you keep it as it is, R you keep it as it is, and you take minus JXC as a common. So you will get R divided by minus JXC plus 1, you will get this one. So we know that minus 1 by J is equal to J and minus 1 by JXC is equal to J divided by XC. J divided by XC is J divided by 2 pi FC. Okay, so J divided by 1 by 2 pi FC. So if you take 1 by 2 pi FC in the numerator, it will be J divided by 2 pi FC. Okay, now just substitute this value, that is minus JXC value, in the above equations and rewrite it. Just substitute above minus JXC, 1 by minus JXC in the above, and rewrite the equations. You will be arriving at this particular. So VA, so Vin as it is, so R will be as it is, minus JXC Okay, you just this equations I have rewritten here. uh, Minus jxc to bracket of r minus jxc plus 1. Okay, so after substituting the 1 by minus jxc value, you will be getting this one. Va is equal to vn into bracket of j 2 pi of rc. You substitute that and simplify it, and r here 1 by jxc, if you substitute, it is j 1 by minus jxc. Okay, just substitute here, we'll be getting this equation. Okay, just to simplify it once again, minus jxc value you substitute, minus jxc value you substitute, you will get this equations. Okay, so now this can be represented as, this can also be represented as, so this is the way. So va is equal to vn into bracket of j as it is, f, this f will be as it is, 2 pi rc, that is fl. So f divided by fl, numerator term, here also the same. So 1 plus j f divided by fl. Fl is, once again here it is given, fl is equal to 1 by 2 pi rc, that is a lower cutoff frequency value. You just substitute fl in this equation, you will be get the same above equation. Okay, this is the potential at the point va. Okay, now we know that inverting configurations of operational amplifier, so v naught is equal to af into va, where af is the gain of the amplifier and va is the input to the amplifier. So v naught is equal to af into va is vn into bracket of this one, substitute va value and just rewrite it. Okay, now just calculate the gain of the filter. One sec, wait for a few minutes. Okay, so if you, this is up to here you understood. Okay, v naught is equal to af into you just va you substitute, and this is the equation for the gain of the filters. Okay, gain of the filter is nothing but v naught divided by vn is equal to the other term. So if you calculate the magnitude of the gain, so af is the gain of an op-amp, and if you calculate the magnitude of the gain, so to eliminate the imaginary terms, so the magnitude of v naught by vn is equal to af into bracket of f divided by fl whole divided by square root of 1 plus f divided by fl square. Okay, this is the magnitude of gain of the first order high pass Butterworth filter. So here there are three cases. First case is when f is less than fl, that means your operating frequency is less than the lower cutoff frequency, then the gain v naught by vn will be always less than the af. Okay, so when f and fl, there are three cases. When f is equal to fl, that is operating frequency is equal to lower cutoff frequency, so the gain, magnitude of gain will be always 0.707 af. These are some constant values. So when f is greater than fl, then v naught by vn, that is magnitude of v naught by vn, is equal to af. Okay, this is the frequency response characteristics of your first order high pass Butterworth filter. Here fl is the lower cutoff frequency, the frequency above this is pass band and frequency below this is a stop band. Okay, so the frequency above fl will be passed from input to output side, the frequency below fl will be stopped. Okay, that is the thing. Okay, this is about the first order high pass Butterworth filter derivations and the problems on this, and other detailed explanations we will take up in next class. Okay, just one important note is you have to carefully see the video. Along with that, I will be sending a PDF copy of the same here, so just after watching the video, just practice the same derivations in the paper. Okay, step by step things is given here, just practice all the things in the paper, so you will be understanding it. If you got any doubt, even after practicing also, you can feel free to contact me anytime. Okay, thank you.